Have you ever just stopped and wondered what actually makes things move? I mean, really think about it. We see it all day, every day. Kicking a ball, a car driving by. It seems so obvious. But for most of human history, what was really going on was a total mystery. Well, today we're going to pull back that curtain and look at the invisible forces that are, quite literally, running our world.
So, what is this secret ingredient? It's something we are dealing with every single second, but we can't see it, we can't touch it, we can't hold it. It's the very thing that can get a 10-ton truck rolling or stop a tiny baseball in its tracks. And that is the question we're diving into today. What is this invisible power? And here's how we're going to tackle it. First, we'll break down what a force even is. Then, we're going to walk through Sir Isaac Newton's 3 legendary laws of motion, one by one. And finally, we'll connect it all back to how these cosmic rules show up in your life all the time.
All right, first things first. Let's get to know our main character for today, force. You can think of it as the invisible push or pull that makes literally everything in the universe go.
You know what's fascinating is that you have never ever seen a force. Not really. What you see are its effects. When you push a shopping cart or pull open a drawer or whack a hockey puck, you're not seeing the force itself. You're just seeing what it does. It's the action that gets things moving.
And force isn't just about starting and stopping. It can also, change the shape of things. Think about stretching out a spring or squishing a foam ball in your hand. That change in shape, that's a direct result of a force being applied. So it's an influencer of both motion and form.
Okay, so this is absolutely crucial. Not every force actually causes a change. Imagine you're trying to push a super heavy box across the floor. The force you're applying is fighting against the force of friction. Now, if your push and the friction are equal, the forces are balanced. They cancel each other out, and that box isn't going anywhere. But the moment you push harder than the friction, the forces become unbalanced. And that unbalanced force is the secret sauce. That's what makes things move.
This whole idea of unbalanced forces leads us perfectly into our first major rule, Newton's first law of motion. I like to call it the law of laziness, and you'll see why in just a second.
Now, before Newton, this guy Galileo had this incredible thought experiment. He pictured a marble rolling down one ramp and then up another, and he realized, wait a minute, if there was no friction at all, that marble, once it hit a perfectly flat surface, would just keep rolling. Forever. It was a brilliant insight. Objects don't naturally want to stop. Something else has to make them stop.
And this tendency, this resistance to change, it has a name, inertia. Basically, an object that's sitting still wants to keep sitting still, and an object that's moving wants to keep moving at the exact same speed and in the exact same direction. It's kind of like the universe's built-in stubbornness.
You feel this all the time. When a car slams on its brakes, the car stops, but your body, because of inertia, wants to keep right on going forward. That's exactly why we have seat belts. They provide that necessary unbalanced force to slow you down along with the car. The same thing happens when a bus suddenly takes off. The bus moves, but your body wants to stay put, so you feel like you're being thrown back in your seat. That's inertia and action.
And here's the key. Inertia is tied directly to an object's mass. I mean, think about it. What's harder to get moving, an empty shopping cart or a full one? The full one, right? That's because it has more mass, which means it has more inertia, so it puts up a bigger fight against any change in its motion.
Okay, so if we need an unbalanced force to overcome all that inertia, the next logical question is, how much force do we need? Well, that brings us to Newton's second law, which is basically the mathematical recipe for motion.
But first, to really get the second law, we have to talk about something called momentum. A great way to think about it is as a measure of an object's unstoppability. A huge truck moving slowly can have a massive impact, right? But so can a tiny bullet moving super fast. That's because momentum combines both mass and velocity into one powerful measurement.
Now, Newton's original wording for his second law sounds pretty dense, I know, but what it's really saying is that force isn't just about changing an object's speed, it's about how quickly you change its momentum.
And all of that complex-sounding stuff, it boils down to maybe the most famous equation in all of physics. Force equals mass times acceleration. F equals ma. Simple. If you want to accelerate a certain mass, you got to apply a force. Want to make it accelerate faster or move a bigger mass? Guess what? You need more force. It's just that elegant.
And we use this law all the time without even realizing it. When a cricket player catches a screaming fast ball, what do? They pull their hands back with the ball. Why? Well, they're increasing the amount of time it takes for that ball's momentum to drop to zero. By stretching out the time, they reduce the acceleration, and that massively reduces the force of the impact on their hands. It's just brilliant, pure physics.
And that brings us to the final piece of this puzzle. It's a law that tells us something profound. Forces never, ever act alone. They always come in pairs. This is Newton's third law. Now, you've definitely heard this one before, but let's really unpack what it means. It means that if you push on a wall right now, that wall is pushing back on you with the exact same amount of force. It's not a delayed thing, it's instant. Forces are always a two-way street.
Here are two perfect examples. When a gun is fired, it pushes forward on the bullet. That's the action. At the exact same instant, the bullet pushes back on the gun with an equal and opposite force. That's the reaction, and we feel it as recoil. Or think about jumping from a small boat to a dock. To jump forward, you have to push the boat backward. Action, reaction.
But wait a minute, you might be thinking, if the force on the bullet and the gun are the same, why does the bullet fly off at incredible speed while the gun just kicks back a little? Well, the answer takes us right back to our old friend, F equals ma. The force is the same, yes, but the masses are completely different. Since the gun has so much more mass, it experiences way less acceleration than that tiny little bullet.
So let's bring this all home. These three laws, they're not just some abstract concepts for a physics class. They are, quite literally, the operating system for our entire physical world.
When you boil it all down, it's this simple. 1. Objects like to keep doing whatever it is they're already doing. 2. If you want to change that, you need to apply an unbalanced force. And 3. Whenever you apply a force, you get one right back in your face. That's it. That's the logic that governs everything that moves.
From the way your body leans when a car takes a turn, to the simple act of walking, which is just you pushing on the earth and the earth pushing back on you, these laws are everywhere. So the question I want to leave you with is this. Now that you know the rules of the game, what are you going to notice differently about the world around you today?